The last reaction type that we'll feature in videos for this module are oxidation-reduction reactions. So our learning goals are going to be to recognize oxidation-reduction reactions and identify which species are being oxidized and which are being reduced in a given oxidation-reduction reaction. So let's first talk about generally what's happening. This is the case where we're going to transfer electrons from one species to another species, and that's the essence of the reaction. So it doesn't sound like a whole lot is changing, but it makes all the difference in the world for those species because they're going to change their charge. Most likely they're going to change their charge. So here we have an example of A with a minus charge reacting with B, and at the end of the reaction A will be neutral and B will have the minus charge. Now it could also be that one of them is positive and the other one becomes positive at the end of the reaction. I'm really just trying to help you follow the electrons. Now these reactions, it's a lot to say oxidation reduction every time you want to talk about these reactions, so a lot of chemists use the shorthand to call it redox reactions. So let's see some examples. Key one is metal reacting with acid. We saw some of this in an earlier video. For example, if calcium reacts with hydrogen chloride is an acid, it will cause the calcium to enter solution. It will dissolve the calcium in the solution and it will produce hydrogen gas. The calcium in this case is being converted from a neutral atom to a positive ion. So something has happened to that calcium. The hydrogen has been converted from basically being a positive ion to being a neutral hydrogen. Whenever something is in an elemental form, like H2, we say that it has neutral charge. It doesn't have any net charge at all. So in this case, what we're seeing is that there's an electron that is transferring itself. Actually, there's a couple of electrons transferring, but an electron is transferring from calcium to hydrogen. This is the essence of the process that's taking place. So when you look at an oxidation-reduction reaction, you're going to look for a change in oxidation state or formal charge as a key signature that something has happened. Now I should also mention that these words, oxidation and reduction, have the following very specific meanings. Oxidation is what happens when an element loses electrons, and reduction is what happens when an element gains electrons. It seems a little backwards, doesn't it? When you figure when you're gaining something, you're not reducing. But you can think of it as reducing the charge. You're reducing the charge, making it more negative, so you had to gain electrons. A good mnemonic for these is called oil rig, which basically means oxidation is loss, reduction is gain. So if you can remember that, you'll be able to keep them straight and always identify what's being oxidized and what's being reduced. Now, in oxidation-reduction reactions, we often can get a handle on what's happening by dividing a given oxidation or given redox reaction into two halves called half reactions. So to illustrate this, consider the reaction of sodium metal with chlorine gas. Okay, this produces sodium chloride. It's actually quite a spectacular, violent reaction. It's really fun to see. And in this process, what's happening with the sodium is that it's losing an electron, so it's forming sodium plus ions, and I've shown the electron explicitly here. And the chlorine is gaining 2 electrons so that it makes 2 chloride ions. Okay, now you can already see there's something that's a little bit out of balance here because sodium's only producing 1 electron, but chlorine needs to use 2 to form chloride ions. Well, we call these two things half reactions. Each of them captures half of the process that's going on in this redox reaction, this oxidation-reduction reaction. So when we balance these half reactions, we want to be sure to balance both the charge and the mass. So if you look at both of these half reactions, hopefully you'll see that charge is balanced because in the first one you've got a sodium plus an electron, which is a minus charge, so it adds up to 0. In the case of the chlorine, we added 2 electrons to a neutral molecule, so we have 2 minus charges on the right-hand side. Now, when we put these together to make the full oxidation-reduction reaction, we're going to want to add them together in such a way as to eliminate electrons from the sum of the half reactions. So that means we're going to have to multiply one or the other, or both, of these half reactions by some integer in order to cause the electrons to cancel out, to have the same number of electrons on one side as we have on the other side. So in this case, I've got chlorine produces 2 electrons. To get 2 electrons in the other half reaction, I'm going to have to multiply through by 2. So I had to multiply 2 sodiums, producing 2 sodium ions plus 2 electrons. Now when I add these two half reactions together, the electron part is going to cancel. And the net result is to produce this reaction, which is the balanced oxidation-reduction reaction. So you can see in this way we can use the half reactions actually to help us balance the reaction. So let's look at what this means, for example, if we have electron transfer between metals. Now I want to note that the oxidation state of a metal, we call it the oxidation state, is actually the effective, it's the actual or the effective charge when it's in a compound. So the way we can figure this out is we almost always say that when oxygen is in a compound, it has an oxidation state of -2. Almost always when hydrogen is in a compound, it has an oxidation state of +1. And the other oxidation states sort of follow from that. So let's consider this reaction between aluminum and manganese oxide. Okay, it forms aluminum oxide and manganese. So what are the oxidation states here? Well, for the manganese in manganese oxide, each oxygen implicitly has a -2 charge. There are 2 of them, so they add up to a total charge of -4, but the manganese oxide molecule doesn't have any charge, so the manganese must be +4 to balance those oxygens. We can do the same thing for aluminum oxide. In this case, there are 3 oxygens, each of whom have -2 charge. So I need to have a +3 on each of the aluminums in order to balance that charge. So now if I were to draw the half reactions for this particular overall reaction, for the aluminum, it's going to go from aluminum, which is neutral, to the aluminum ion plus 3 electrons. And for the manganese, it's going to go from manganese in a +4 oxidation state, where I have to add 4 electrons to result in a neutral manganese on the right-hand side. So now when I take these 2 half reactions, I want them to eliminate totally the number of electrons that are up here. So in order to do that, I'm going to have to multiply through by 4 on the top, which gives me 4 aluminum plus 4 aluminum ions plus 12 electrons. And for the bottom one, I'm going to have to multiply through by 3, which gives me 3 manganese ions plus 12 electrons, giving me 3 manganese atoms. Now I can add these together to form the full reaction, and I get 4 aluminum plus 3 manganese plus 4, going to 4 aluminum 3 plus 3 manganese ions. 3 manganese atoms. So this now gives us the clue for how to balance this overall chemical equation. If I simply apply these numbers in front of the various species that are in the skeleton equation above, I'll end up with this chemical equation. And you can verify that this in fact does balance the oxygens. For example, on the left-hand side, I've got 3 of the manganese dioxides, which gives me a total of 6 oxygens. On the right-hand side, I've got 2 aluminum oxides, which gives me a 2 times 3, or 6 oxygens over there. So everything is balanced in this resulting equation. Now I want to revisit for just a brief moment combustion reactions, because they are actually an example of an oxidation-reduction reaction. Let's look at methane combustion as an example. Okay, now for oxidation states, methane, H is +1, so that means in methane the carbon is actually formally -4. It doesn't actually form a -4 ion, but we think formally it is a -4 in this case. In carbon dioxide, oxygen is -2, so formally speaking, the carbon has a +4 charge. So we can see that in this case, we have changed the oxidation state of the carbon. Now in O2, since that's an elemental form, we say that oxygen has an oxidation state of 0 there, but it has an oxidation state of -2 in carbon dioxide, so it too is contributing to the oxidation reduction going on here. So if I were to create the half reactions in this case, I'm going to end up going from C4- to C4+, and I'm going to go from O0 to O2-. So which one is the oxidation and which one is the reduction? Can you figure it out? Who's losing the electrons? Losing electrons is oxidation. Okay, well, the carbon has to lose the electrons, so it is the thing being oxidized. And the oxygen is the one gaining electrons, so it is the thing being reduced. So you may want to try a couple of oxidation-reduction reactions and see if you can identify the oxidized and the reduced quantity. I will say in all combustion reactions, carbon is being oxidized and oxygen is being reduced. So that should be easy for you to remember.